Sailors have reported an ocean that glows solid white, like the sea is lit from underneath. Not sparkles, not flashes, a steady, milky sheet out to the horizon. It's called a Milky Sea, and it's rare enough that most people assume it's CGI. But it's real. In 2019, a massive event south of Java was visible in low-light satellite imagery. At its largest extent, the glowing region reached about 100,000 square kilometers. That's not a bay or a beach trick. That's open ocean biology on a scale big enough to leave a faint signature from orbit. So tonight we're doing the science version. What it is, how satellites detect it, and why bacteria are the leading suspect. Most people hear glowing ocean and think of tourist videos, where the water flashes blue when you disturb it. That's usually dinoflagellates. You kick the surf and you get sparkles. Milky Seas don't behave like that. Witnesses describe a continuous glow spread across the surface, even when the sea is relatively calm. It's less like glitter and more like a dim, milky light sitting on the water. That difference matters because it points to a different biological engine. If the light were only wave-triggered, it would appear in streaks and bursts. Instead, Milky Seas look switched on over wide areas. They're also hard to film. Wrong exposure turns the glow into plain gray water. So bright blue sparkles can be real, but they're usually not a Milky Sea. Milky Seas are offshore, massive, steady, and rare. Milky Seas usually show up in the open ocean, not tucked into a protected bay. And one region comes up again and again in modern satellite-era work, the eastern Indian Ocean around Indonesia. The 2019 event sat immediately south of Java. What matters is the setup. A Milky Sea isn't just glow. It's a bloom that has to spread and persist instead of getting shredded and diluted by mixing. Think of a surface layer that stays coherent long enough for microbes to build density. In the 2019 case, the glow was detected from late July into early September and it spanned 2 lunar cycles, which helped low-light sensors get cleaner looks during darker windows. That doesn't mean the ocean glows there all the time. It means the geography and the physics can set the stage. When that stage is set, the ocean can do something that looks impossible, quietly, far offshore. A satellite doesn't see a Milky Sea the way your eyes do on a ship deck. Sensors like the day-night band on VIIRS are built for extremely faint night signals, the same kind used to observe city lights and other low-light sources. That matters because the open ocean is normally close to black at night. So if a huge patch emits even a dim, uniform glow, the pattern can stand out. But detection is fragile. Clouds can hide it completely. Moonlight can wash out contrast. And reflections off the ocean surface can produce look-alikes that have to be ruled out. That's why good detections are rare and why the strongest detections tend to be the biggest events. In NASA's analysis of the 2019 Java case, the glowing area reached about 100,000 square kilometers at peak, large enough to be visible as a diffuse signal in night imagery. Big is the story. So what's producing the light? The leading hypothesis in scientific work is luminous bacteria, not the usual wave-triggered dinoflagellate sparkle. The first satellite paper on Milky Seas argued the emission was consistent with luminous bacteria, and it specifically discussed Vibrio harvey as a likely suspect in earlier sampled events. Here's the key behavior that makes the steady sheet make sense: quorum sensing. In Vibrio harvey, bioluminescence is controlled by chemical signaling that depends on population density. At low density, light output stays low. As density increases, those signals accumulate, gene expression shifts, and the population can switch into much stronger coordinated light production. That switch behavior naturally fits eyewitness descriptions. The ocean looks simply on, not triggered by waves. It also fits why the biggest events are the ones satellites catch. If only a small patch glows, it disappears into darkness from orbit. But if a surface bloom gets massive and uniform, the ocean becomes a dim lamp across huge distance. We still lack routine sampling because the events are offshore and rare, but the biology gives a mechanism that scales. If bacteria can glow, why don't we see Milky Seas constantly? Because the ocean usually ruins the conditions. Winds mix the surface layer. Waves stir it, currents shear it apart. For a Milky Sea to form and persist, you need a surface layer that stays coherent long enough for microbes to reach high density and stay distributed over a wide area. You likely need the right nutrients and organic material too. And even if the event happens, you still need darkness to notice it. Moonlight reduces contrast. Cloud cover blocks satellite views. and most ships never cross the right patch of ocean at the right time. That combination of biology plus physics plus luck is why Milky Seas show up in reports for centuries but still feel like folklore. They're not impossible, they're just logistically hidden by the size of the ocean and the rarity of the perfect setup. Here's the biggest problem for science: you can't study what you can't reach. Satellites can flag candidates, but for years surface confirmation was rare because research ships weren't there. That changed with a documented boat encounter during the 2019 Java event. A yacht passed through the region and recorded on-deck views that matched the satellite detection, supporting that the signal corresponded to real light on the water. That matters because it upgrades the story from interesting pixels to confirmed phenomenon. But it also shows why Milky Seas remain partly unsolved. By the time a detection is noticed and shared, the event may already be changing. Even if it persists for weeks, you still need instruments and samples from the right part of the globe. So Milky Seas sit in that frustrating space where we have strong evidence they exist, but we still don't have routine, repeatable sampling of the chemistry and biology. Even with the right sensor, detection is tricky. The day-night band is ultra-sensitive, but it's fighting noise, moonlight, airglow, clouds, and reflections. A Milky Sea doesn't look like a crisp outline from orbit. It's a diffuse patch that can be faint and uneven at the edges. Analysts have to rule out lookalikes, especially thin cloud features and changing illumination conditions. That's why the most convincing detections are usually the biggest, most uniform events. Small Milky Seas might be real and still never show up in satellite data. This is also why the 2019 case is so important. NASA's analysis describes it as visible from late July into early September, spanning 2 lunar cycles, which created darker windows where the signal could be detected more consistently. So when you hear visible from space, don't imagine something bright like a city. Think barely detectable, but real, because the patch is enormous. Quick myth control: Milky Seas are not underwater lava. They're not a chemical spill glowing like paint. They're not electric water. And they're not the same thing as the wave-triggered sparkles you see near shore. Milky Seas are offshore, wide area, and steady. Also, the real thing is usually subtle on camera. If a clip looks neon blue and perfectly uniform, it may be heavy color grading. A genuine Milky Sea is often described as pale, milky white light with natural fall-off into darkness, and cameras struggle to capture it cleanly. So the best way to judge a claim isn't the vibe, it's the context: open ocean location, continuous glow, and ideally supporting satellite detection in the same region and time window. Milky Seas aren't just a cool visual. They're a clue that biology can organize at massive scale in the open ocean. If luminous bacteria are coordinating light through density-dependent signaling, they're also coordinating chemistry and behavior across a surface water mass. That points to specific ocean conditions where the surface layer stays unusually stable and productive. It also matters for Earth observation. VIIRS was built to detect very faint light at night, and Milky Seas show that, in rare cases, satellites can detect biological light over open water. That opens a practical path: combine low-light detections with curated report databases to improve prediction, then send ships to sample events while they're active. The 2019 Java event matters because it persisted across many nights and reached an area on the order of 100,000 square kilometers, large enough to give a real sampling window if you know where to look. That's how a myth-looking phenomenon becomes a repeatable field target. Here's the clean takeaway: Milky Seas are rare events where the ocean surface emits a steady, milky glow across huge areas. They're different from the wave-triggered flashes near shore. In the most famous modern case, NASA analyzed a 2019 event immediately south of Java that persisted from late July into early September, spanning 2 lunar cycles. At its largest extent, the glowing region was about 100,000 square kilometers. The leading explanation in scientific literature is biological: luminous bacteria, with density-dependent signaling that can switch communities into coordinated light production. What we still don't have is routine sampling, because these events happen far offshore and don't announce themselves. So Milky Seas sit in the perfect Atlas unfiltered zone: real, measurable, visually insane, and still hard to fully pin down. That's why the internet keeps mistaking them for CGI.